Hello. In today's video, we're going to talk about osmosis briefly and then bring up the idea of osmotic pressure and how it's going to be affected by adding a solute into a solvent. So first, let's just go over what osmosis is. So osmosis is going to be the net movement of a solvent through a semi-permeable membrane. Okay, so that movement is going to occur towards a solution with a greater solute concentration. And it's going to occur until the concentration on both sides of the semi-permeable membrane are equal. Just as a note, if you don't know what a semi-permeable membrane is, it is going to be a membrane that allows certain things through, semi-permeable. So we're going to allow small uncharged particles to pass. Such as water. They will block large molecules, such as solute molecules or ions, from passing the membrane. Okay, so here is an image of what's going on in osmosis. So here we have a lower solute concentration. These brackets mean concentration. And on this side we have a higher solute concentration. And we're going to have water flow in this direction until we equalize on both sides. Okay? So that movement of water causes what's called osmotic pressure. So this is going to be pressure on either sides of a semi-permeable membrane due to the flow of water. Okay, so there's some other ways of defining osmotic pressure. We can also call it the pressure that must be applied to the solution in order to prevent osmosis from occurring. And it's also considered the pressure of the excess fluid once concentration on both sides are equal. But just note that if we have a so osmotic pressure itself is based on our solute particle concentration. And the greater our solute concentration, the greater our osmotic pressure. Okay. So the equation we use so osmotic pressure is basically a large pi sign. So our osmotic pressure is equal to I, our Van Hoff factor, times by number of moles divided by volume, times by our gas constant, times by our temperature. Now this number of moles out of the volume can be rewritten as molarity, right? So I MRT. So this is our osmotic pressure. This is our Van Hoff factor, which is literally in every equation except for our Raoult's law. M is molarity. R is our gas constant. And this one specifically is going to be the 0.08206 liters times by atmospheres over moles times by Kelvin. So our temperature must be in Kelvin. Okay. Now, we have the ability to do reverse osmosis. So we're going to reverse the flow of osmosis. So instead of having our solvent move towards less or greater solute concentration, we're actually going to have the opposite occur. So the net movement of solvent through a semi-permeable membrane towards the solution with the lesser solute concentration. Again, opposite of what we generally think of. And we can do this by applying a pressure greater than the osmotic pressure on the solution. Okay, we use this idea of reverse osmosis to purify things. So here is just a diagram comparing osmosis versus reverse osmosis. So we can see here On our left side, we have a lower solute concentration, right side on a greater concentration, so the right solution would have a greater osmotic pressure. If we want to reverse osmosis, we're going to apply an external pressure on the concentrated solution, and that will cause our particles to push back through in our solvent molecules to push back through reverse from what we generally think of for osmosis. This is almost always considered a technique for purifying contaminated water. So if you look on the back of a Dasani bottle, it'll say purified using reverse osmosis techniques. We actually have a reverse osmosis instrument here at UNG. So it's used in order to purify a lot of times. So you can take contaminated water, take a semi-permeable membrane, and just push the clean, uncontaminated water through, and all the contaminants themselves will be stuck behind. Okay? So we can take the ideas of concentration of solute and use what's called relative solution terms. So we're going to look at three terms. We have solutions that are considered isotonic to each other. So isotonic solutions are going to be one who have the same osmotic pressure. So in this case, our rate of transfer of solvent molecules would be the same on both sides of the semi-permeable membrane. And then we can look at what's called a hypotonic solution. So this is one that has a solution with a lower osmotic pressure. And as such, it has a lower solute concentration. So the rate that the solvent leaves the solution is greater than the rate it enters. Okay, last we have hypertonic. So a hypertonic solution is going to be one. Sorry, let's move this a little bit. Is going to be one where our we have a greater or higher osmotic pressure. And since it has a greater osmotic pressure, it means that it has a greater solute concentration. Since it has a greater solvent concentration, it'll have a rate of solvent leaving the solution, or sorry, going into the solution is greater. Okay, So let's look at those three ideas. So if we have an isotonic solution, the rate that the solvent enters and leaves both solutions on both sides of the semipermeable membrane will be equal, so there will be no net flow of water. But the water will flow in and out, or back and forth between the sides of the, or between the the two sides of the semipermeable membrane. If we have a hypotonic, which is the first one I talked about, or the next one I talked about, hypotonic, we have a solute concentration that is lower, so it has an osmotic pressure that is lower. So this is the hypotonic solution out here. This is the, if it's hypotonic on the outside, we consider the inside to be hypertonic. But if we have a hypotonic solution, the water is going to leave the solution quicker than it enters. Okay, and then here is our hypertonic solution. With a hypertonic solution, we have a greater solute concentration, greater osmotic pressure. So in order to kind of equalize that, you have to have the rate of solvent going into that hypertonic solution being greater. Okay? So we usually kind of think of these idea of isotonic, hypertonic, and hypotonic in terms of red blood cells. Which I will call RBCs. These, if we take them, we can take and look at them. They are separated, or sorry, they have a semipermeable membrane. So that semipermeable membrane holds all the stuff inside the red blood cell, and we can then, sorry, red blood cell looks like this, kind of a little divot. This is the semipermeable membrane, and inside the red blood cells, all the cellular things that you have inside, and red blood cells are going to be within a bloodstream. So our bloodstream itself has a specific osmotic pressure associated with it, and we want to make sure that our red blood cells are going to be in a isotonic solution, right? So if we place a red blood cell into an isotonic solution, there will be no net flow of solvent molecules. So if you've ever had to get fluids, you probably ask yourself why you got a saline solution as opposed with just water, if you need hydration. But it's because when you add that into your blood, you need a solution that is going to be isotonic with your red blood cells, which is why you have a case where you have salt or saline within the water that they're pumping into you. Okay, so if we were instead to place a red blood cell into a hypotonic solution, so hypotonic, that's going to have a lower osmotic pressure than the red blood cell. In this case, we are going to have the solution has a lower osmotic pressure and lower solute concentration. So as such, we're going to move water from that lower concentration into the red blood cell. So the water, or the solvent, will flow from the solution into the red blood cell until osmotic pressures are equal. Or until the red blood cell bursts, called hemolysis. So if there's a great enough difference between those osmotic pressures, the water will keep flowing in until it bursts. So if we can't get to a point where the osmotic pressures are equal, then they will burst. Okay? Our other option is hypertonic solution. Here we've got a greater osmotic pressure. So a greater solute concentration. So the red blood cell will have a lower solute concentration, so you're going to want the solvent to flow from the red blood cell into the solution. And this will occur until the concentrations level out, right? And it could, in fact, keep on occurring if they don't level out until they shrivel up. Or the red blood cell shrivels up. That process is called crenation. Okay. Here's what that would look like. Hypotonic solution, we're going to have a net gain of water into the cell, which will cause that hemolysis if we can't reach a equal osmotic pressure on both sides. With our hypertonic solution, the water is going to leave the cell until we equalize concentration or until it crenellates. Both of these are very bad for cells. Or if we're isotonic, we're good. It's just going to go at the same rate. Last thing I want to talk about within here is just some calculations. So since this is the end of our colligative properties talk, I want to talk about calculations for molar mass. Okay, so using the changes in property. So looking at those colligative properties, we can actually go through and calculate out our molar mass. So molality is the first thing we're going to look at. So remember, molality is used in boiling point elevation and freezing point depression, right? So we can relate molality in both of those, and we can use that idea of solving for molality in order to solve for our molar mass. So we can solve for molality by rearranging our colligative properties equations. So arranging the boiling point elevation equation, we get molality is equal to our boiling point elevation over I times by our molal boiling point elevation constant. So once we have molality, so if we solve for molality, we can then use the molality which is moles of solute over kilograms of solvent. We can take that and multiply that by kilograms of solvent, and that will be equal to our moles of solute. Okay, so after we've solved for our moles of solute, we can then take our mass in grams of our solute, divide it by our moles of our solute. That'll give us our molar mass of solute. Okay, so if we have our mass, so in order to use this, we have to have our mass of our solute, our mass of our solvent, and our boiling point elevation. Okay, we can also use molality. So we can solve for our molality by taking our freezing point elevation equation and rearranging it. Okay, so once we solve for our molality, we can then multiply that by our kilograms of solvent, and that will give us our moles of solute. That moles of solute, we can then again take our mass of our solute, divide it by our moles of our solute to get our molar mass of solute. Okay, so that's using molality. We can also use molarity. Molarity is used when we're solving for our osmotic pressure. So we can take our molarity and set that equal to our osmotic pressure divided by IRT. So again, just rearranging that osmotic pressure equation. Once we solve for molarity, remember that molarity is our moles of solute over our liters of solution. So we can take that and multiply that by our liters of solution. And we can solve for our moles of our solute. Okay, then if we have our mass of our solute in grams, we can divide it by our moles of our solute, and that will give us our molar mass of our solute. Lastly, let's look at mole fraction. So our mole fraction, that is used in our Raoult's law. Alright, so molarity, osmotic pressure, forgot to write that. It's osmotic pressure equations. Okay, so Raoult's law, we're going to have to do some weird things, but remember that our mole fraction of anything, such as our solvent, is equal to the moles or our solvent we can rearrange to our pressure of our solution divided by our pressure of our solvent. So if we want to solve for our moles of our solvent, we can just set it equal to our solution vapor pressure divided by our vapor pressure of our pure solvent, right? Because that's usually what we're going to be able to actually solve for in this case, because this is something that will be given and this is something that will be given. After we've done that, we can solve for our solvent, and then using that idea, we can solve for our moles of our solute by taking our moles of our solvent divided by our mole fraction of our solvent. Okay? And then from there, we subtract our moles of our solvent. So using this will give us our moles of solution. And then we subtract out our moles of solvent to get our moles of solute. Once we have our moles of our solute, then we're just going to take our mass of solute in grams divided by our moles of solute, and that will give us our molar mass of solute. This is a little bit different way of approaching it. On the top ones, we are trying to directly solve for our solute. Here we have to go through our solvent first, because our mole fraction of our solvent can be determined using our vapor pressure of our solvent. So since we know our vapor pressure of our solvent in these cases and our vapor pressure of our solution, we can then solve for our mole fraction of our solvent. Then using that idea of the mole fraction of the solvent, we can use that to determine our moles of our solute by taking this ratio, which gives us our moles of our solution. Okay, that is everything. You guys have a great day.